All right. So let's zoom out again to the big picture. What are we doing here? We've talked about probabilities, defined them in terms of population data. We've talked about how the population data set can be abstracted away to something called distribution, or distributions have density functions, and you can work with those things to get at probabilities. We've talked about code that you can use to generate data, to generate samples from the population. So I want you in your head to kind of imagine these things as all different views on the same object. So really there's just the distribution of these variables in the population. And you can think of that as the population data set. You can think of that as code that you can call upon to draw samples. You can think of that as a density. But all of it is representing some kind of source of data. So when you have a data set that you have in your hand, it's a sample. It does not represent all of this stuff. It's just one sample. So it's like you clicked on run on your R code and it gave you 100 samples, right? That is not the whole population data set. That's just a subset of it. Or that's not the whole density. That's just some draws from a population that has that density. So these things are all kind of the same thing, different views, different perspectives on the same object that are more useful to work with in different settings. You need to be able to think kind of very flexibly to solve problems and work either with densities or imagining a population data set to kind of be able to derive some, by analogy to counting, how certain things should work, or write code that samples data so you can test whether something works out. All of this together, sometimes you'll see people call them just data generating process, or DGP. DGP, distribution, population data set, population, all kind of like the same thing. It's just something out there in the world, which is where your data comes from. There's a barrier, right? You never get to access this like hidden reality. You just have your little data set. And all of that stuff over there, remember, is actually imaginary. It doesn't exist. There's, most of the time the population is not even so clearly defined, but you have to imagine it's there in order to talk in any kind of concrete way that anybody can understand what it is that you're trying to say. We all have to have the same kind of shared imagination, same kind of shared abstraction, so that we can communicate productively. And I think I showed a picture before of like, this is all the stuff that's under the surface, like the 90% of the iceberg. This is the 10% of the iceberg, or 1% even. That's above the surface, and it's what you have to work with. But really, you care about the whole iceberg. And okay, so just to summarize what we did today a little bit, in one picture, we have here the joint density. From the joint density, if we add up along axes, we get marginal densities. If we take a slice of the joint density and we scale it up, we get the conditional density. And the same picture for continuous random variables. If you have the joint density, if you sum up along axes, we get marginals. If we take a slice and scale it up, we get conditional. And the thing to remember about these pictures is not so much the process, because the process of getting one from the other, again, you can get to that by thinking about the probability, like thinking about it in this discrete case, and thinking about how to count things the right way to get what you want. If you had a population data set, and that will give you all of the equivalencies and whatnot. But what I actually want you to really remember is that the joint distribution is everything. If you have the joint distribution, you can get all the other stuff. And so everything is really about, when we start talking about the assumptions as we go further in the course and start talking about the assumptions that we have to make about to get a particular method to work or to be unbiased, and we're going to talk about what that stuff means, but those assumptions are always going to be assumptions about the data generating process, about the overall joint distribution or some part of it, like some conditional distribution. But really what matters is what is the joint distribution of your data. And of course you don't know, but you have to make some particular assumptions about ruling certain cases out, because if you don't, then your method may not work as advertised. So that's where we're going. It's necessary to have these abstractions, because otherwise we cannot talk about concretely what those assumptions have to be. What is it exactly that we're trying to rule in and rule out? Once you have those abstractions, then you can concretely relate them to the real world and say, oh, this is a case where I believe this is true and that's not true. But unless you have those abstractions, making those connections is impossible, which is why we have to go through all of this first to get there. So hopefully that makes sense, and you're not, too bored or like, why are we doing this stuff? I don't understand. I've never seen a density before in public health, blah, blah, blah. Hopefully it comes together in the later part of the course. So that's it. I'll see you next week.